Okay, so we want to prove by induction that if you were to add this sequence of numbers, right? If you have this series here, that you could do this computation much faster just by using this formula, 2n squared minus n. And so whenever we do a proof by induction, there are 3 steps. Step 1 is what we call the base case. So let's run through these together. So step 1 here, it's called the base case. And for the base case, usually you let n equal 1. So if n equals 1, that means that we're going to add together the first 1 term. Like if n was 7, then you would add the first 7 terms. Like this is 1, 5, 9, 13. And we know they're just adding 4. Like the next one would be 17, 21, and so on. So if n was like 30, you would add together the first 30 terms, which can take a while. So instead of adding the first 30 terms, you would just plug in 30 in here. But the point of this video is to prove that this actually works. So let's just pretend that we were adding together not the first 30 terms, not the first 20 terms, just the first 1 term. So if n is 1, well, if n is 1, then it's not like 1 plus 5. It's not going to be, because it's literally just the first term, which is just 1. But what happens if you plug 1 into the formula here? Because this is the formula there. So notice what we get here. We would get back 2 times 1 squared minus 1, which is 2 times 1 minus 1, which equals 1. And this agrees with the fact that the first term is 1. Right? So I'll just put it like, I'll just put over here the purple 1, where this purple 1 is this guy, and this red 1 is what I got back when I plugged in 1 into here. So the base case holds true. So that's always the first step, where you plug in 1 into the equation and show that whatever you get from the equation is equal to the first object here, the first term itself. Now, step 2 is where we say this. We assume that the formula holds for n equals k. This is always how this works. So for step 2, let's assume that the formula works for not just the first term, not just the second term, but for the first kth terms. So what we can do is this. Let's assume that 1 plus 5 plus 9 plus 13 plus ... plus 4 times k minus 3 equals 2 times k squared minus k. So let's jot that down here in blue. So step 2 is to assume that the formula works for up to n equals k. So we're going to assume that all of this is true. So this is our assumption that this here is true. And the way that you finish these proofs by induction is with the 3rd step. So let me actually just text this in. So the 3rd and final step is to do this. Show that the original formula works for up to, or just works for n equals k plus 1. You see, because if we assume that the formula works for n equals k, and if you can prove that the formula works for the next number, then that means that the formula is going to work for everyone, because k is generic. It can be any number of terms. And if you can show that the next one works, then it's always going to work. And so what we're going to do is we're going to, you see this original formula up here. You see this n there and this n there. We're going to replace both of these n's by k plus 1. Now here on this side, what I'm going to do is I'm going to go 1 plus 5 plus 9, and I'm going to extend it all the way to the k plus first term like this. So what we're trying to show is we're trying to prove that this is true, right? So I'm trying to prove this. So what I want you to see is that here in green, all of this there, from 1 plus 5 all the way up to 4k minus 3, that's what we assumed to be true from step number 2. And all of that there equals the 2k squared minus k. So by substitution, all this stuff in green gets replaced by 2k squared minus k. And then I have plus from this guy here. And then I have in parentheses 4k plus 1 minus 3. And it's somehow, some way, it's supposed to equal this gibberish here. So all you got to do to finish this proof is just to show that this actually is true. So why don't you simplify the left and simplify the right? And so if you simplify each of the two sides, you do get back a true statement. So this is how proof by induction works. Step 1 is the base case where you show the formula works for n equals 1. Step 2, the induction step or the assumption step, is where you assume that the formula works, but you write it instead of n, you write it in terms of k. And then step 3 is you have to prove that the formula works for up to n equals k plus 1, which is when you go to the original formula and you expand it up to the k plus first term. And then you write the right-hand side in terms of k plus 1. And then you do use a substitution from step 2 into step 3. So try a couple of these problems and you'll get the feel for it. They're very repetitive in terms of the approach to them, where you use a substitution from step 2 in your third step. And then it's algebra, algebra, algebra. And so this is how you do a proof by induction.